Okay, so last time we introduced the 2 points Gauss-Legendre formula, and we said that it will present the advantage of selection of the 2 points x0, x1 different than the ends of the trapezoid, which will give us a higher order of accuracy for the computation of the integral. Why? Because we can see that if we have the freedom to choose these 2 points, x0 and x1, and determine their locations, then we will end up with 4 unknowns instead of 2. So now, if we compute the integral as c0 of x0 plus c1 of x1, since we have the freedom to select x0 and x1, so we have now 4 unknowns, c0, x0, c1, and x1. To find these 4 unknowns, we can write 4 equations. And these 4 equations will impose on our function to have an integral, the integral of the linear function to be equal to the exact integral of 4 functions. The first equation will be by saying that the integral will give the exact value of the integration of a constant function. The second one will give the exact prediction of the integral of a linear function. The third one will give the exact value of the integral of a quadratic function. And the fourth equation will be obtained by imposing to have for a cubic function the same integral. So this will be our 4 equations with 4 unknowns, which will allow us to find what should be C0, X0, C1, and X1 to satisfy these 4 conditions. So we have developed last time together what are these equations, if you remember. So we started by setting that C0 of x0 plus C1 of x1 should be equal to integral from -1 to 1 of 1 dx. We got the first equation. Then we move to say now the second condition is to have a perfect match with the integral of a linear function. So by writing now that c0 of x0 plus c1 of x1 is equal to integral between -1 of x dx, and since fx is defined as x, then fx0 is equal to x0 and fx1 is equal to x1. And we did integration between -1 and 1 of x dx, which is equal to 0. Now keep in mind that we are doing these conditions for an interval of -1 and 1, but of course we can generalize this result as you will see together in the coming slides. Whatever is the interval, I can use this method. We'll see how. So this is the second equation. The third equation now will be obtained by imposing that the integral of a quadratic function of the form of x squared will give the exact value by doing c0 of x0 plus c1 of x1. So all we have to do is to replace fx0 by x0 squared and fx1 by x1 squared and integrate from -1 to 1 x squared dx, which will give us 2 over 3. This is our third equation. And finally, the fourth equation in this case is just obtained by saying that the integral must be exact also for a cubic function x cubed. And now fx0 is x0 cubed and fx1 is x1 cubed. And if we integrate between minus and 1 the function x cubed dx, we will get a value of 0. So now we are ready with our 4 equations. We have the 4 equations. So we have a system and we can solve it to get our unknowns. So if you solve, you will get the following, that C0 and C1 are equal to 1. And your x0 and x1 are -1 over radical 3 and 1 over radical 3. So now you can say that if you want to use the 2-point Gauss-Legendre formula, also called Gauss quadrature, okay, you can be sure that your method will give you exact results if your function is constant, linear, quadratic, or cubic. And if you have a higher order, this method will reduce the error compared, of course, to the trapezoidal rule because it's third order accurate. Despite that you are using a linear function, you are obtaining a third order accurate integral. So you gain 2 degrees of accuracy because you have the freedom to select the 2 points x0 and x1. And it was shown that the optimal location is to have x0 equal to minus 1 over radical 3 and x1 to be equal to 1 over radical 3 with coefficients c0 and c1 equal to 1. Okay. Now, in order to generalize this method, to be able to use it, whatever is your interval, we will see what to do. So the above derivation was based on a domain of integration between minus 1 and 1. And this domain has a length of 2 and is centered around x equals 0. So if you want to apply a Gauss-Legendre formula to non-normalized domains, we need to do a transformation of variables. How this is possible? It's simple. If we take this example here, we want to find the integral of fx over this domain. We have the length of the interval is 25 minus 1 is equal to 24. And then we say that if we displace this curve, okay, if we slide it along x, the integral will not change because this area will remain the same. Okay, so if you say I will just slide it parallel to x in order to center it at 0, all I have to do here between 1 and 25, the center is at 13. So I should move my curve backward a distance of 13. So the extremity 25 will be now at 12. 13 will be exactly 0. So now my interval is centered at 0. And 1 will become minus 12. And I didn't did any change in the integral because the area, since I did it just sliding parallel to x, the area will remain the same. Now, the idea is to get interval minus 1, 1 is to normalize my my interval from minus 12 to minus 1, 1. So how can I do this mathematically and still obtain the same result of my integral? All I have to do is to do transformation of variables. So the idea is to say I have an initial interval between a and b, and I want to transform it to an interval of minus 1, 1 without changing the value of integral. How can I do this? I can say I want to define a relation between x and the transformation variable xd in a way that x is obtained as a1 plus a2 times xd. Okay? A1, if you want, will play the role of sliding of your curve, and a2 will play the role of normalization. Okay, so here, if you get a1, a2, you can change variables from x to xd. And this is very simple to do because when x is equal to a, xd should be minus 1. And when x is equal to b, xd should be 1. So by applying these two conditions, you can get what should be a1 and what should be a2. So all we have to do is to apply a system of two equations with two unknowns. So when x equal to a, xd equal minus 1. When x equal to b, xd equal to plus 1. We replace into the transformation of variable equation, which is x equals to a1 plus a2 xd. Then we say that the first condition will give us that a is equal to a1 plus a2 times minus 1, while the second condition will give us a second equation, which is b equals to a1 plus a2 times 1. Now we end up with a system of two equations with two unknowns. The two unknowns are a1 and a2. So by solving this system, we get that a1 should be equal to b plus a over 2, while a2 should be b minus a over 2. And then by replacing a1 and a2 by their values in the transformation equation, we can say that x, variable x, should be replaced by b plus a over 2 plus b minus a over 2 times xd, while dx should be replaced by, if we do dx here, then we have, this is a constant, so dx is equal to b minus a over 2, which is a constant, times dx. And now, after performing this change of variables, now we will end up with the evaluation of an integral between minus 1 and 1. So we can go back to the result we have demonstrated together in the case of Gauss quadrature formula. So we have developed together the two-point Gauss quadrature formula. We have seen that if we can normalize the interval and having it centered at 0, so it's minus 1 from minus 1 to 1, then we can apply the rule that exact integral, if I have a constant, linear, quadratic, or cubic function is given by f of the point we have found. So it's, I think it was 1 over radical 3, I think. Let us check it here. Yes, it was, the first one is minus 1 over radical 3, the second one is 1 over radical 3. So once you normalize your interval, you can use this formula, okay? So, and this is xd0, and this is xd1. So you should transform first your function to a function of xd, the transformed variable. Once you have this function, then you can, all you have to do is to replace in this function xd first by minus 1 over radical 3 to get f of minus 1 over radical 3. Then to replace xd1 by 1 over radical 3, and you add the two results to find your integral. Now, in case your function is to the power 4 or to the power 5, you don't expect an exact value, but of course it will be a much better error than the case of trapezoidal rule, because the trapezoidal rule is first order accurate, while the Gauss quadrature method, the 2-point Gauss quadrature method, is third order accurate. So now in this example, we have a function to the power 5. So we expect to get a much better result than the trapezoidal rule. And now we can compare the true relative error that we will get. So now all we have to do to be able to apply the formula we developed together is to do the change of variable. So first, we should do x equal to b plus a over 2 plus b minus a over 2xd. Here, a is equal to 0, b is equal to 0.8, and we do b plus a over 2, which is 0.8 plus 0 over 2, which is 0.4, plus 0.8 minus 0 over 2, which is 0.4. So now x should be replaced by 0.4 plus 0.4 xd. Now concerning the x, which is the derivative, if you want, the elementary variation of x dx, should be related to dxd. So all we have to do is to apply dx is equal to b minus a over 2 times dxd. By replacing b and a by their values, 0.8 and 0, we just get that dx is equal to 0.4 times dxd. And now we can say that by using the transformation of variable, I can write my integral, instead of integral from 0 to 0.8 of fx dx, I can write it as integral between minus 1 and 1 of fxd dxd. Okay? So this was my purpose at the end, to transform it to a form that I know how to integrate. And now all I have to do is to use the result I developed previously, which is that this integral, using the 2 points Gauss quadrature formulation, is equal to f at minus 1 over radical 3 plus f at plus 1 over radical 3. And of course, f, if you want to not confuse, I will call it f d, okay? Because it's of course not this function. So it's not this function. I should transform it to be function of xd and then replace. So now all I have to do is to just replace x by, in my expression of fx, I should replace x by 0.4 plus 0.4 xd. And once done, also I should replace dx of the integration by 0.4 dxd. Then I will transform it completely to a function of xd times dxd. So I can replace, I can find for minus 1 over radical 3 and 1 over radical 3 what is f. Okay? So this is the whole method I should do. So now all I have to do is to say that integral between 0 and 0.8 of my function times dx is equal to 0.2 plus 25 times, I replace now x by 0.4 plus 0.4 xd, minus 200, again I have x, so I replace it by 0.4 plus 0.4 xt squared, plus 675 times 0.4 plus 0.4 xd So each x I have in my formula will be replaced by 0.4 plus 0.xt. So I should replace also x4 and x5. Okay, and I should not forget to replace also the x by its expression function of dxd, which is 0.4 dxd. And now when I am done with this, I will end up with a new function times dxd. This is my whole function. Okay. Now, in this function I obtain, this is a function of xd. I should replace xd by minus 1 over radical 3 the first time, and then f of 1 over radical 3, then say that the integral is equal, the approximation of integral using the 2 points Gauss quadrature is equal to f of minus 1 over radical 3 plus f of 1 over radical 3, which gave me a value of 1.822578. And now if I calculate the true value, already we have the true value from before. If you compare with the true value, we will of course have an error that is much lower than the one with trapezoidal rule. The trapezoidal rule, if you remember, the error was 90%, the true relative error at the first iteration, when we just consider trapezoidal without composite method. Here, all we did is that we used, you can compare if you want, just now with 90%. The true value was 1.6 something. So it's clear the enhancement, the improvement in the computation. Now, if you do the true relative error, it's relatively much smaller than 90%, of course. Okay, so it's nearly close to 2 over 1.6. 0.2 over 1.6, okay, which is smaller than 10%. Okay, so it's 1 over 8, okay, which is good. Compared to 90%, it's much better. It's 100 over 8%, which is close to 10%. It's a little bit larger than 10%, but still much smaller than 90%. Now, if I want to, yes.
بس ال 0.4 تبعية الدي اكس
Yes.
ما لازم تنضرب بكل الانتجرال؟
بلا أكيد، ما هي كلها هيك like this. Yes, of course. We should add brackets here. Okay?
Yes, thank you, doctor.
Okay. So, now, if we want to enhance more expectation, here we have it, since we have order 3, our 2-point Gauss quadrature can give exact value up to order 3. Okay, if you want to enhance the method, we can use, instead of 2 points, 3 points Gauss quadrature. Okay, because now we were able to reduce, now using 2 points, we were able to reduce from 90% error to approximately around 10, little bit larger than 10%. Okay, but still we can improve more. If we can improve for this function, we can improve 100%, because if I add 1 point, then I will add 2 orders of accuracy. Why? Because now if I say, instead of considering just 2 points, I will consider 3 points and try to find what will be the resulting formula of Gauss quadrature. Now, when just you add 1 point, you will add 2. Why you will add 2 degrees of accuracy? Because you are adding 2 new unknowns. Your 2 new unknowns are C2 and Fx and X2. So instead of just writing your integral as C0 of x0 plus C1 of x1, you will write it now as C0 of x0 plus C1 of x1 plus C2 of x2. And since you have the freedom to select your point in a way to give you the optimal result, okay, then you will add 2 equations. And what will be the added 2 equations? If you remember, when we had just 4 unknowns, we said the first equation will impose to have exact integral for constant function. The second will impose to have exact integral for the linear function. The third equation will impose to have exact integral for the quadratic function. The fourth one for the cubic function. Now we will add 2 equations. One to ensure same integral for x to the power 4, and 6th equation will ensure to have same integral for x to the power 5. So now if you develop this method and you find what are the coefficients C0, C1, C2, and what are x0, x1, x2, if you now apply this technique to the example we did together, you expect an error of 0. Okay, and let us verify this. So now all we have to do, if you want to have a more exact value, is to increase the number of unknowns. So instead of dealing with 2 points, we will deal with 3 points randomly selected in a way to ensure. So we have the freedom of selecting them. So we have 3 points and they should satisfy 6 equations. So let us write together the 6 equations they should satisfy. Again, we follow the same procedure. Okay, please try to do it as practice. So the first equation, you will get it by saying that I will impose to have for a constant function the same value of integration. So you will get a relation between the first equation will relate C0 and C1. Okay. The second equation, you will get it by saying that I want to have an exact integral for a linear function. The second one you will get it for a quadratic function. And now if you have a integral of x3, you should have the exact result. And the additional 2 equations will be that the integral of x to the power 4 should give me this result, and x5 should give me the following equation. So now I will end up with 6 equations with 6 unknowns, and if I solve this system, I will get the following result. What does this mean? This means that if I want to compute the integral using this 3-point quadrature, Gauss quadrature technique, I should write the integral as C0 of x0 plus C1 of x1 plus C2 of x2. And now, since I solved my system, I optimized the location of my points to get the better approximation for the integral. Then all I have to do is to replace. So what is C0 here? C0 is 5/9. Fx0 is f at minus radical 3/5. C1 is 8/9, so plus 8/9 times f of x1. X1 is 0, so plus f of 0. And finally, plus C2. C2 is 5/9 times f at plus radical 3/5. And now I will apply this on the same example, and I will see the reduction of error. Of course, now I can expect an error of 0 because I'm using this method is accurate to up to order 5. Okay, it's accurate 100% up to order 5. So what is nice here again, that you are using just a linear function of order 1 that will allow you to reach a certain integral value of order, and the accuracy is of order 5. So by just selecting 1 point more, if you have the freedom to select 3 points, you will increase your accuracy from 1 to 5. Okay, so now all I have to do is to apply it in this problem. We will apply this method. Let me check if you have questions. Okay, so yes.
ليش بالفورمولاز قبل بالايكويشنز ما كان في 2 x2؟
لانه قبل نحن في several schemes للجاوس quadrature. You can take 2 points, you can take 3, you can take 4. كل ما تزيد number of points you will select, كل ما تصير الاوبتمايزيشن اصعب، بس كل ما الريزلت تصير more accurate.
قصدي هون بهيدا الاكزامبل يعني فوق لما عملنا 6 equations ما كان في 2.
ما كان في شو؟
C2 and x2.
ما عم بفهم السؤال، سوري. Can you repeat؟ ما كان في x2؟ لا
هيدا السلايد.
ايه اوكي.
اللي بعدها. في ايه إنه هون ما في بالإيكويشن C2 X2.
Okay, yes, I see what you mean. Sorry, yes, بيكونوا عاملين typing error. Look, I will derive them with you again. Okay, ما بدها شيء.
بس
Let
هو
us write.
كله نفس الشيء يعني، بس مع C2 وX2.
Yeah, بيكونوا مغلطين
Okay.
بالسبسكريبت. Okay, let us do it for example. يعني ما بدها شيء، خلينا نعمله. عندنا نحن الإيكويشن هي C0 okay fx1 plus sorry C0 fx0 plus C1 fx1 plus C2 fx2. اوكي، خلينا مثلا نعملها اول شيء على الكونستنت equation. اذا عندنا constant function يعني هي 1, so if we take fx to be 1, okay, then replacing x by 1 here بتكون fx1 1 و fx2 1 و fx0 1. تطلع اول equation C0 plus C1 بدنا نزيد هون plus C2 okay plus C2 equals to the integral from -1 to 1 of 1 dx اللي هي 2. So I will update all of these equations for you بال PowerPoint that will be posted على Blackboard. Okay, so here plus C2. If we apply for the second equation هتكون C0 x0 plus C1 x1 plus C2 x2. If we apply for the third هتكون plus, so we should add here plus C2 x2 square, and here we should have plus C2 x2 cube, and here it should be plus C2 x2 to the power 4, and this is C2 times x2 to the power 5. It was George who asked the question.
Yes, doctor.
Thank you, George. Okay, so this is by solving this system, but solution is right. Okay, yani this is right, but just I forgot in the slide to put some terms. So now, if I want to use these coefficients, all I have to do then is to do the transformation first. So here the transformation is the same. We are using the same transformation procedure to transform the integral from an integral between a and b to an integral between -1 and 1. So you will get, since you are using the same function, the transformation will be the same. Okay. Now just what will be different is that now that you are using 3-point Gauss quadrature. So now when you replace here, okay, all you have to do is to compute after finding xd, and here also of course it's brackets. مثل ما حسن قال. So we have brackets here, and we multiply all this term by 0.4. So now you have that the integral is, this is C0, 5/9, times f of x0. This is C1. This is x1. This is C2. And this is x2. So as we said, for when we use the 3-point Gauss quadrature method, okay, we'll have C0 equal to 5/9, x0 equal to minus radical 3/5, C1 equals to 8/9, x1 equals to 0, C2 equals to 5/9, and x2 equals to radical 3/5. Now all we have to do is to replace in this function. And don't forget تاخدوا مع ال 0.4 كل هيدي fxd. okay, all of this يعني ال fxd مع ال 0.4 اللي هي تبع ال transformation of dx. okay, so now in this equation you start by replacing xd by minus radical 3/5, you get your result. Then you replace xd by 0, you get f of 0, and then you replace xd by radical 3/5 to get f at radical 3/5. And now once you have these three numbers, you can compute your integral. And as expected, you have 1.64053. So you just have this error because of round-off errors. And due to the round-off error of the calculator, you will see that epsilon t is 10 minus 13, but actually it's 0. Okay, so just here we obtain a certain error due to round off error of the machine, not because the method is not 100% accurate. The method will give you 100% same result, but due to round off errors, we got a true relative error of 4 times 10 to the power minus 30. So you can compare, of course, you can see the huge decrease. Trapezoidal rule كانت 90%. If we want to calculate exactly بالprevious step لازم نحط the exact value, so we can compare with this. If you compare with this, and this is the exact value nearly, you can see تقريبا هي بالorder of 10% when we did the 2 Gauss quadrature. And now when we use the 3 Gauss quadrature technique, we got an error of 0, because when we use the third quadrature, it's accurate up to order 5. Okay, and to start to have an error, the function should be x6, x7, x8. Okay, any question on this? Okay, so look, we are done with chapter 20. So now we will move to the last chapter. So please, if you have questions before, because I want to close this session to start the new chapter. Any question on what we did, or anything about this chapter? Okay, so yeah, I will open a new session to go over the last chapter.